All right, so we're starting on page 15. All right, so c doesn't equal to 0. We'll let c be the constant. Then the limit as x approaches c. So the first thing we do with any limit problem, especially if we're approaching a real number, we just go ahead and do substitution, right? See what that gives us. Okay, so c in for x. So I'm just substituting c in for x, and I'm getting 0 over 0. So that tells me I could factor, but typically, especially if L'Hopital's rule is available, we prefer L'Hopital's rule. It's just a little bit faster. So we can find the derivative of the numerator and denominator separately. Now make sure that we treat x as the variable and c as the constant. Okay, so as we do our derivative here, sorry, I want to keep reminding us that we really want to use arrows. Obviously, it's not going to be a big deal for me, but on the AP exam, free response, especially with L'Hopital's rule, just use arrows instead of equal sign, so you don't just have to deal with that issue of them deciding whether to give you credit or not, or take off points or not. Okay. All right, so derivative x cubed becomes 3x squared. C cubed, we don't say 3c squared. Okay, c cubed is a constant, so constant goes to 0. Give me 1 second, guys. All right, so substitute c in for x. I'm sorry, we're derivative still. So x cubed becomes 3x squared, x squared becomes 2x, and c squared becomes 0. Okay. Reevaluate the limit. Now that we've done L'Hopital's rule once, as soon as we do L'Hopital's rule once, we want to reevaluate. C in for x, and we get 3c squared over 2c. Reduce, we get 3c over 2. Okay, L'Hopital's rule. Any questions? Okay, number 2. If 3x squared minus 4xy equals 1, then when x equals 1, dy dx equals. So there's a lot of things going on here. We definitely know there's derivative involved. But as we look at this equation, there's more than just power rule going on. There's power rule for 3x squared, but hidden within this 4xy, we have to understand that there's product rule, and then there's also implicit, because we see y kind of mixed into the equation here. It's not cleanly by itself. So let me write out a couple of things here. We got to make sure we are aware and that we apply product rule. Make sure that we understand this is implicit. And also be careful with the negative. This negative, once we expand this product rule out, this negative has to distribute to both terms. Okay, so let's find the derivative first and see what else we need to do after that. Okay, so 3x squared becomes 6x minus parentheses set up my product rule here. And then careful, 1 goes to 0. All right, f prime g, my f is 4x. My g is y, so 4x becomes 4 times g. G is the original. Back to f, and then g prime. So y's derivative is 1. Make sure we don't forget to attach dy dx. Let's do some cleanup here. Solve for dy dx. And divide both sides by negative 4x. So now we're looking at this saying, well, I have the derivative, so why isn't this matching up with the answer choice that's given to me? And the reason why is because they're asking for a bit more than just the derivative equation. They're asking for the slope. So I see x equals 1, which is good. I can plug 1 in for x, but the issue is when I plug 1 for x, there's still this y left over, and we need the y value so that we can get it down to a number. So we need to kind of look back and see, okay, how can I get that y value that I need to insert into both the x and y so I can get my slope? Well, we know order pair comes from the original function, so we have to kind of backtrack a little bit and insert 1 into the original equation so that we can actually get the order pair that we need. So this derivative requires more than just an x. It needs x and the y, but they only gave us x, but we have the equation to kind of figure out what that y value is. Okay, so we're going to also need to find the y value. Okay, so we'll insert 1 in for x. Okay. Subtract 3 from both sides. Y equals 1/2. Negative 2 over negative 4. Okay, so now that we have both the x and y value, we can move forward and actually get to the slope for my derivative. So I typically use this notation to indicate that I'm about to insert my full order pair into my derivative. Okay, 4 divided by 2 is 2, 2 minus 6. Negative 4 over negative 4 equals 1. So the slope of this curve at order pair 1, 1/2 is a steepness and slope of 1. Okay, questions? All right, number 3, the function f whose derivative is given by f prime. Has a local maximum at, so we have to understand that as we graph this, we're looking for the maximum from a derivative perspective. Okay, so we're not going to look at the peaks and valleys. We're going to look at the x-intercept for relative max. But we can graph this out. I can also show using the 36 Pro, but graphing calculator first. Zoom 6. But if you look at your answer choices are only between -2 and 2. So we can really adjust our window that way, right? There's no need to extend all the way from -10 to 10 if we're only looking at between -2 and 2. So I'm going to just give myself a little bit more room here. Let's go from -3 to 3. You guys can always play with your windows, but you're only playing with these 4 numbers. Yeah, let's see what that takes me here. And it's a lot cleaner here because I'm looking at my derivative graph. I really only care about these x-intercepts, right? These x-intercepts is going to tell me where my relative max, relative min are. So okay, remember, you're looking at the derivative graph. So label accordingly here. Whatever's above is positive slope. Whatever's below is negative slope. Whatever on the x-axis is where slope is 0. Okay, but really, a relative max is going to be where, if you can imagine these being critical points, it's going to be where your slope changes from a positive to a negative. Oh, I'm sorry. This extends to -2 here, so I should be going down here as well. Okay, so if I find these 3 critical points here, if I do second trace 0, but really I only care about the critical point that goes from a positive to a negative, right? Positive, negative, because I want a relative max. So relative max is going to have to be from a positive slope to a negative slope. So where the graph changes from above to below the x-axis. So really I only care about this point right there. So I'll pick a point to the left of the x-intercept, hit enter. Pick a point to the right of the x-intercept, hit enter. Hit enter again. Zeroes in on 0.511. So 0.511 is going to be the only point where there's a relative max. I found the other points as well, but really the relative max is going to only occur at 0.511. Okay, you can also get to this without a graphing calculator, but it's just a little bit more cumbersome on the 36 Pro. If you go to table, okay, table, edit function. Second option here. Type in the function here, 5x cubed minus 15x plus 7. Hit enter again. Maybe I can start at -2. And step, maybe you can do step like 0.1 just to kind of have, just be able to get through this. If we want to be more accurate, we can always make it 0.05 or 0.01, but it just takes too long to scroll through. Okay, hit enter. So what you're trying to do is you're looking at the y values, and you're trying to see where's the y value going to change from a positive value to a negative slope. So I'm looking for where it will change from a positive to a negative slope. And right now, these are all positive values, positive values. Positive, still positive. There it is. You see that between 0.5 and 0.6, we see that there's a change from a positive to a negative. and that's what's occurring here. So we know there must be a relative max here. Now, let's say there were choices that were even closer where it was like 0.51 versus 0.52, and you didn't know which one. You can always go back to table, edit function. Okay, this time you can just go ahead and start at here. Oh, that's nice. They picked up where you left off, and then you can make your step even smaller here. You can make it 0.01 if you want, just to kind of get more accuracy so that it'll step through a little slower. And then you can look to see where is that sign going to change. That sign is going to change right around 0.51. Okay, so that kind of gives you a bit more accuracy. If you want even more accuracy, you can do 0.0001. Okay, but typically that's enough for us too. This takes a little bit longer, but we can still do it. Okay, so f of x equals the integral from 0 to x of h of t, where h is shown above. Okay, so what is this relationship here? Well, we know that f and h are not at the same level, okay, because it takes the antiderivative of h to make it even rise up to the same level as f, which means that h is sitting at a level below f, okay, because it needs the help of this in order to even make it equal. So if h is sitting one level below f, what we know is that h is really f prime. Okay, so that's the relationship here. We have to know that this is telling us that this is really h prime. Okay, another way that you can do this is, okay, you can find the derivative of both sides and kind of convince yourself that way. The derivative of f of x is just f prime, and the derivative of integral will just, these two operations cancel out. I'm just left with h. Okay, so this h, okay, this f, okay, h is really f prime. Okay, this is the h graph, but it's also f prime. Okay, so we understand, okay, we're looking at the derivative graph, which could be the graph of f, right? So we know we have derivative graph here. Let's label and gather information. Anything above is positive slope, below is negative slope. On the x-axis is slope 0. We have A here. I just want to just identify some points and just name it so that we have some anchor points. I'll call this B, I'll call this C, and I'll call this D. And so for my slope sine line, starting at 0, my critical point is going to be at B and D. That's going to be where my slope is going to be 0. Okay. So to the left of B, positive slope. Between B and D, negative slope. To the right of D, positive slope. So we know that this is going to be the shape of the graph. The graph is going to rise to a max, decrease to a minimum, and rise again. Now, from the derivative graph, we can also gather information about concavity. So the peaks and valleys will be the points of inflection, right? So we have A being a relative max. We know that's a point of inflection. C is a relative min. That's a point of inflection. So to fill out our concavity sine line, we look at our slope. Wherever my f prime is rising, that's going to mean concave up. Wherever my f prime is decreasing, that's going to be concave down. Rising, concave up. Okay, so we're going to just create a graph that has these behaviors. So I know that at B, I want some relative max. At D, I want some relative min. So I like to sketch my graph before I even deal with concavity. And I know that A is going to fall somewhere between 0 and B. So I'm just going to plot a point along the curve. C, we know is the point of inflection. It's going to have to land somewhere between B and D. So I'm going to just target that point there. All right, so we have our relative max, relative min figured out. Let's do our points. Let's do our concavity here. We know that from 0 to A, we're dealing with concave up. So now I'm going to force a concave up shape into my graph. Between A and C, concave down. And then from C onward, concave up. Now, we're looking at our answer choices, and A is out. B is out. That's not showing concave up. But C and D look very similar, and E is definitely out. And I think on my answer choice, my key, I think I selected D, but I think it's wrong. I think it should be C. And the reason why is this. You see at A here, that could be a point of inflection, right? Concave up to concave down. But look at here, though. This is a slope. This is a slope undefined. So if it's a slope undefined, at A, it shouldn't be showing whatever that number is. It should be showing 1 or 0. It should be showing, undefined. It should be a hole there, right? Because there shouldn't be a slope that exists here, because that's a vertical tangent line. I think C is going to be the better choice here, even though I think I picked D on my answer key here. Right, and even though the way I drew it, it looked like D, but we know that if this is the original graph, that slope should not be undefined, because if it's undefined, it shouldn't be showing up as whatever this number is, whatever is 1 or 2. All right, number 5. Which of the following is the interval decreasing? Okay, so there's a problem that you can obviously plug in the calculator and actually tell, but this is part of a non-calculator, so I'm looking for work. I'm looking for students to show that are they able to go through the steps, first derivative test, sine line. Okay. Okay, so first derivative test, find f prime, set f prime equal to 0. And then once you find your critical points, populate your sine line, and then test your intervals. Okay, power rule. One goes away to 0. Okay, once you find your derivative, set equal to 0. Factor out a GCF. And then once you have your factor form, set both parts equal to 0. Take the square root. Don't forget, there's a plus or minus that shows up. Okay, so this is roughly around plus or minus 0.707. Okay, just so that it's easier to pick numbers on our sine line. Okay, so to the left of negative 0.7, I'll choose negative 1. Between negative 0.7 and 0, I can choose negative 1/2. Between 0 and 0.7, I'll choose 1/2. Between the right of derivative 2, I'll choose 1. All right, so once you have your critical points and your test points, you can insert into the derivative and gather information. Okay, so negative in for x, that's negative 1. Negative 1 in for x here, that's 4 minus 3 is positive. Negative times positive is negative. Okay, next interval, negative 1/2. 2 times negative 1/2, that's negative. 4 times negative 1/2 squared, that's going to be 4 over 4. That's 1. 1 minus 3 is negative. Negative times negative is positive. Next up, 1/2. 1/2 in for x. 2 times 1/2 is 1. 4 times 1/2 squared, that's 4 times 1/4. 1 minus 3 is negative. Negative times positive is negative. And finally, 1 here, 2 times 1, positive. 4 minus 3 is positive. 2 positive makes positive. Okay, so decreasing will be in these two intervals. Okay, from -infinity to -3/2, √3/2, and then from 0 to √3/2. Okay, let f be the function given by f prime, and let g be the function given by g of x. I'm sorry, not f prime, just f of x. At what value do the graphs have tangent lines that are perpendicular? So tangent lines that are perpendicular, that means we want to figure out at what points are the slopes going to look like that, where the slope of the tangent lines are going to be opposite, are going to be perpendicular, or where the slope is going to be opposite reciprocals of each other, right? So for instance, perpendicular would be, slope of 1 versus slope of -1/2, right? So we're going to set up that situation where we'll let f prime equal to -1 over g prime. Okay, so this will ensure that I'm going to find a situation where the slope will be opposite reciprocals of each other, right? If I just did f prime equals g prime, then I would be looking for where the two points where the slope is going to be parallel to each other. But here I'm looking for points where the slope is going to be opposite reciprocals of each other. So I'm creating that rule to begin with, and then working from there and solving for x. Okay, so this is my starting point here. So f prime is going to be chain rule here, 2 parentheses x minus 4 outside derivative times inside derivative. And then g prime, that's just going to be e to the u times u prime, so e to the 3x times 3. Okay, so we'll replace f prime and g prime with what we found, and then kind of just find a way to solve for x. F prime -1 over g prime, 3e to 3x. All right, I'm just trying to figure out how I can solve for x. This is going to be kind of hard because we have x's all over the place. It's hard to solve by hand, but maybe what I can do is I can just get everything over to one side. I'm going to cross multiply first just to get rid of the fractions. All right, so that's really messy here, but what I can do is I can just graph this. Okay. And look to see where is this graph going to cross the x-axis. So wherever cross the x-axis means I've solved for x that will make this equation true. And once I solve for x, I have found the value that can work. Okay. Just to kind of understand that, it's good, you can graph it, but there's also a way to brute force this. Once you have this, you could do this, you could plug in each of these values in here and see which one actually works. Okay. But I'm going to go through the way I think they meant for us to do this, and that's just to graph it into the function. Yeah, I think I have a different variation on my key here, but as long as we can get 0 on one side, any variation will work. Okay, so it looks like amongst my answer choices is going to be this point here. I'm going to just make my window just display values that I care about. So let's say from -2 to 2. Okay, so that's the only critical point that I see. So I'm going to do second trace, option choice 2, 0. And I'm going to look for that x-intercept, choose a value to the left of that x-intercept, hit enter. Scroll to a point on the other side of the x-intercept, hit enter. Hit enter a third time, -1.14. Okay, let f of x equal cosine of 3 pi x squared. Find f prime of 1/3. Okay, so f of x is cosine of u. And if I want to find f prime of 1/3, I first have to find f prime. So going to go through chain rule here. Cosine of u becomes negative sine of u times u prime. Once I have my derivative, go through substitution, place every x with 1/3, and see if we can find the slope. Okay, so 1/3, that's 1/3 squared is 1/9. 3/9 is 1/3. So 1/3 pi, or pi over 3. Positive, not negative. Okay, so unit circle values. Sine of pi over 3 is √3/2. Keep the negative there. 2's cancel out, -√3 pi. Okay, find the value of the derivative of f inverse at 2. We practiced this yesterday, right? Make our chart, work our way around the chart. We know 2 is the x value of my inverse function. If we know 2 is the x value of the inverse, we know 2 must be the y value of my f of x. So we're going to work backwards here, see if we can figure out the x now that we know what the y value is. Okay, bring everything over to one side, have 0 show up. All right, this is not something that we can factor, but we can kind of guess and check our way, trial and error our way through solving for x. So let's always just start with 0 and find numbers that are close to 0. So start with 0, 0 plus 0 minus 2, that doesn't work. That does equal to 0. So if I tested 1, 1 plus 1 is 2, 2 minus 2 is 0. Okay, that works. So I'm going to use 1. I know my order pair is order pair 1, 2, which means on the inverse side must be order pair 2, 1. Okay, but this is really what I need to find. So if I can find f prime of 1, if I can find the slope of the graph at 1, then I can use that slope value to turn around and figure out the slope of the inverse at its corresponding point. So f prime of 1, we first have to find f prime of x. Okay, go through power rule. X to the 5th becomes 5x to the 4th, x becomes 1. Find the slope at 1. 1 to the 4th is 1. 1 times 5 is 5. 5 plus 1 is 6. So if the slope of the f graph is 6, then the slope of the inverse is going to be 1/6. Okay, make sure that you don't change the sign, that you're just doing the reciprocal here. Okay, graph of the function is shown. Let h be defined as h of x equals x plus 1 times f of x. Find h prime. So first things first, we need to find h prime of x. To find h prime of x, we need to be able to recognize that, oh, these are two separate things being multiplied together. If I want to find the derivative of something that has a multiplication in between, I got to go through product rule. Okay, so f prime, x plus 1's derivative, we'll let this be f, we'll let this be g. X plus 1's derivative is just 1. G is the original. Back to f. And then g prime is second term's derivative. All right, so now that we have our derivative equation built, we can take to our next step, find h prime of 4. Place every x with 4. So f of 4, we're going to rely on the graph here. And also we can rely on the graph for f prime of 4. So f of 4 is just a y value at 4. So the y value at 4 is 4. That's my y value. Okay. 4 plus 1 is 5. F prime of 4 is asking for the slope of this graph at 4. Slope is rise over 1, so I'm just going to pick 2 points along this line. It's going to be the same slope anywhere on this graph here, on this line segment. So rise over 1, down 2 over 1. That's a slope of -2. So 4 minus 10 is -6. Okay, question so far? Okay, we're starting off with a spherical balloon. We're given the volume equation. We know this is related rates. We see time kind of scattered all the way throughout, referenced all the way throughout this problem. If I go ahead and find the derivative here, just to see everything show up, v becomes dv dt. 4/3 pi stays. And then r cubed becomes 3r squared dr dt. Threes cancel out, 4 pi r squared dr dt. All right, got some information here. Balloon is being inflated at a rate of 3 cubic inches per minute. Cubic inches per minute, we know that's volume related. Cubic inches per second, you know there has to be time involved. So this must be talking about dv dt. And also it's being inflated, so we know that must be increasing as time passes. So we want that to be a positive. So dv dt positive 3. Radius is 5 inches. Determine the rate of change of the radius. So we're looking for dr dt. Right, so we have everything in front of us. We have the equation, we have the derivative, we have every variable accounted for. The only thing missing is dr/dt, so then we can just plug in. So 3 goes in for dv dt, 5 goes in for r, and we're just trying to solve for dr/dt. Okay, so 3 goes in for dv dt, 5 goes in for r. Do a little bit of cleanup here. 5 squared is 25. 25 times 4 is 100. 100 pi. Divide this over. Now, careful. The 100, as you divide the 100 pi over, the pi is going to stay in the denominator. Okay. And then just enter this in the calculator. Get that decimal value. 0.0095 is closest to 0.010. All right, number 11. Sine of x over 2, there exists a number that satisfies conclusion of mean value theorem. Okay, so we'll step through mean value theorem, which says I'm going to find the slope between the endpoints. I'm going to set that slope equal to the derivative and solve for x and see where on this curve is there a slope that matches the slope between the endpoints. So first things first, I'm going to find my slope. Well, here's mean value theorem, but I'm going to have to take it one step at a time. I'm going to first figure out my slope. So I'm going to take my endpoints, insert into my function one by one. No derivative yet. I'm just finding my order pairs here. So if it helps, so that you don't deal with looking at a fraction and then dealing with the fraction, you can always think of sine of x over 2 as sine of 1/2 x. It makes it a little bit cleaner and easier to deal with the complex fraction. Okay, so really this is sine to the power of 4. You know, sine to the power of 4 is √2 over 2. So it looks like this is, you see how the order pairs are the same? We could call this Rolle's theorem, but we know Rolle's theorem is technically under mean value theorem. So it just so happens that this is specific enough where it could be Rolle's theorem because the order pair is the same. And we know that the slope between the endpoints was going to have to give us 0. So I'm just going to go through the slope process anyways. If these numbers were different, we would still go through this process. So the slope is just change in y over the change in x. And we get 0 over pi, which is 0. Okay, so we know we're targeting a slope of 0. And now that we have the right side accounted for, we're going to work towards the left side. We're going to find the derivative of sine of x over 2 and set the derivative equal to 0 and solve for x. Okay. So I want to think of it as sine of 1/2 x. So the derivative of sine of 1/2 x, sine of u becomes cosine of u times u prime. There's my derivative. There's the slope I'm trying to target. I'll set these equal to each other. Right, my derivative set equal to the slope between the endpoints. All right, if I divide both sides by 1/2, the 1/2 goes away. I can do inverse cosine to isolate that 1/2 x by itself. Where's cosine 0? Cosine is 0 at pi over 2, 3 pi over 2. I can list out a few things here just so I can have some options because I'm going to still deal with that 1/2 at the end. So cosine is 0 at pi over 2, 3 pi over 2, 5 pi over 2. Okay, multiply everything through by 2 in order to get this 1/2 to go away. Distribute 2 through, 2 divided by 2 is 1, so I get pi. 2 divided by 2 is 1, I get 3 pi. And then 2 divided by 2. That's the only option that shows up in my answer choice. Okay, derivative function is given on what interval is f decreasing. So we can graph this function and just simply look to see where is it dipping below the x-axis. Okay, so once you graph, same as before, you would go through your calculator and find your x-intercept, and then look to see where is my graph below, because when it's below the x-axis, that means where slope is negative. So I know it's going to be in this interval here and also in this interval. Okay, so between 0 and 0.633 and between 4.115 and 6.916. Now, in your 36 Pro, you can also do the same thing here. Type in the derivative function. Type in the derivative function, and then just simply look at your y values and see where is my y value going to stay negative. Okay, wherever it stays negative is going to be where my interval is going to be. So you can scroll all the way through, and then you can see that anywhere that's between 4 and 6, your y values will be negative, and so you know you're going to keep that interval there. And once it turns positive, then you know you're going to stop. Okay, linear approximation for number 13. Here's my function. So this is, okay, so it says estimate the square root of 0.95. Okay. I would present it not this way. I would just say, use the decimal 0.95. Okay, I won't let that be as confusing as that. So we know that we have to go through our process, find our order pair first, and then our slope. So A is basically quote unquote our x. So our order pair is f of 0, which is square root of 1 plus 0, which is square root of 1, which is 1. So order pair 0, 1. Slope, to get to the slope, we're going to get to the derivative. To get to the derivative, let's set this up. Chain rule. Do a little bit of cleanup. Now I can evaluate my slope at 0. Okay, so order pair 0, 1. Slope is at 1/2. Point slope form. Once you have point slope form, then you can insert your decimal to your equation. Okay, does not match any of my choices there, so 1.475. All right, one more thing I want to go over that I think will be beneficial. I asked that you guys review pages 1 through 8, because these are also derivative topics. But I'll point out a certain problem here. Number 14. If you have a piecewise function, this is page 4, number 14, piecewise function that tells you that the function is differentiable, that's telling you two things here. It's actually telling you it's continuous and differentiable. So how is that helpful for a piecewise function like this? Well, the issue is we have two missing pieces of information, right? We're missing C or missing D. So if I'm trying to solve for two unknowns, I really need two equations. And the two equations is going to come from the fact that we know our function is continuous. Now, it only says differentiable, but we have to understand that is the understood information here is that it's connected and smooth. Right? It can't be smooth without being connected first. So our function is continuous, but then our function is also differentiable, smooth curve. So what does that entail? That entails that if my function is continuous, I know my graph has to be connected. And if my graph is connected, that means these two segments must share the same y value at 2. So we can set the two expressions equal to each other. At x equals 2. Right, we know that these two graphs, they must meet at the same point at x equals 2 in order for it to be differentiable, which must mean it must be continuous. Okay, so that's one equation that's going to help us at least build something. Differentiable means that's a smooth curve. So smooth curve means there not only is there a transition from where the graph is going to connect at the same y value, there also must be a transition where they must share the same slope at 2, because if they don't share the same slope, then what could happen is you're going to get a sharp turn. But if there's a nice transition from and the fact that they share the same slope at the same point, we can guarantee a smooth curve. So that means they must share the same slope, which means that their derivatives must be equal. So that allows us to create a second equation so that these can help each other out. Okay, so we can find the derivative. Cx becomes c, and d goes to 0. So we're treating c and d as constants here. So it's like 4x plus 1, right? If it's 4x plus 1, the derivative would just be 4, and the 1 would disappear. Same thing here. Cx becomes c. X squared minus cx. X squared becomes 2x. Cx becomes minus c. And there's our second equation. And this is also at x equals 2. So this is an easier equation to solve because I can just merge the c's together and replace x with 2. So if I know the c value is 2, I can use that to help me figure this out. So first I'm going to replace 2 and for x. I'm sorry. And then we also just found the C value. I can insert C or 2 in for C and solve for D here. Four minus 4 is 0. So D equals -4. Okay, so we have C and D, and then the final thing is asking for C plus D. Which is -2. All right, any questions? All right, there are no questions, then I will see you guys in class. You can always text remind me if you have a question before class. All right, thanks guys. See you in class.
Mr. Yang,
Yes.
I had one question on the number 4 from the review.
Yeah. Oh, from today's review?
Today's review, yeah. So you said it could be choice C, but at choice D, it changes concavity at point A. So I'm just wondering why it's still C.
I think
Because
at
in the
C,
timeline, you said
doesn't the
it
concavity also change at A?
does it.
So you know it has to, I think this is concave up, and this is concave down. This is concave up. I mean, it's very gradual, but there is still a change in concavity, right?
Oh.
It's just not as pronounced as this. But the issue here is that, you know, see that slope there? That slope is undefined. If the slope is undefined, it shouldn't be showing up as a value on my derivative graph.
So at the point of inflection, the slope is undefined.
I'm sorry?
So where would the slope be undefined on my graph?
If the slope is undefined on the derivative graph, it should look something like this. It should, you know, look something like this, where that value should not be defined. Because right now, A is looking like a slope of, that's a value of, okay, let me just assuming that it's a value of 1. Right, this is too steep to be a slope of 1.
Oh,
right? That's
okay.
a slope of undefined, right?
Got it. So you just like sort of approximated it and found that out.
Yeah.
Cool. Thank you.
All right, see you in class.
Yep.